For decades, the standard for intermediate force in French law enforcement was the classic 44mm Flash-Ball. The Flash-Ball fired a simple, spherical, homogeneous rubber projectile. A sphere holds a distinct terminal ballistic advantage. No matter how many times it rotates in flight, it always presents the exact same uniform surface to the target upon impact. But the demands of modern law enforcement pushed a transition toward rifled 40mm launchers. These fire aerodynamically complex, non-spherical projectiles, relying on a rigid plastic body and a deformable nose, spinning to maintain accuracy. In the field, these newer systems function as optics-integrated tactical platforms, a departure from the simple, smoothbore launchers used for decades. To classify these weapons as legally less lethal, manufacturers and administrations rely heavily on static kinetic energy thresholds, routinely capping the energy limit at a strict 150 joules. However, moving from a simple sphere to a stabilized cylinder introduces physical variables, like spin rate and center of gravity, that the basic equations for less lethal force were never designed to handle. Because a 40mm round is cylindrical, it requires gyroscopic stabilization to maintain a straight attitude during flight. Internally, these projectiles are split into two working parts: a rigid plastic body that engages the barrel's rifling, and a deformable shock-absorbing nose designed to mitigate blunt force damage. Achieving a stable flight requires a precise mathematical match between the launcher's barrel twist rate, the projectile's center of gravity, and its axial momentum. If those variables do not align, a kinematic failure occurs. The projectile loses stability, yawing and tumbling through the air, ultimately striking the target at a high angle of obliquity. When a round hits sideways, the front-mounted shock absorber misses the target entirely, turning a designed safety mechanism into useless dead weight. To observe exactly how these variables affect injury potential, we analyze an experiment conducted on a block of ballistic gelatin protected by polyaramid folds to simulate a lightly clothed human target. We start with Projectile A, mass 60 grams. Its dense front perfectly places its center of gravity in the middle. Projectile B, 33 grams. Its honeycombed front shifts its center of gravity to the rear. Both projectiles are fired from the exact same rifled 40mm barrel, maintaining identical experimental conditions. Projectile A achieves zero obliquity. It hits nose first, and the front shock absorber compresses directly against the fabric, absorbing energy exactly as designed. Projectile B fails to stabilize. It tumbles and strikes sideways, bypassing the shock absorber entirely and transferring its impulse through the rigid plastic body. Projectile B's specific mass distribution caused an external ballistic failure, altering its terminal threat profile. To quantify these physical differences, we isolate the very first 350 microseconds of target interaction. This chart tracks the loss of velocity over time. Projectile A slowed down steadily, while B's velocity rapidly drops. Its tumbling orientation presents a large surface area, acting as an immediate physical brake. That drop in speed translates into deceleration. Projectile B creates a sharp deceleration peak compared to A's smoother curve. Evaluating injury potential on deceleration alone is a mathematical trap, because Projectile A has almost twice the mass of Projectile B. Projectile B stops faster, but to understand the physical damage inflicted, we have to calculate the actual mechanical forces at play. Applying Newton's second law, we convert deceleration into a force over time graph. Here, the impact's reality is clear. Despite weighing half as much, Projectile B's peak interaction force actually exceeds A's by over 20%. To measure the total momentum transmitted, we look at impulse, the integral of force over time. Projectile A delivers 60% of its momentum in a steady, controlled manner. Projectile B sheds over 80% of its momentum in the exact same window. Converting these areas into solid rectangles contrasts the sustained delivery of A against the sharp shock of B. The tumbling impact concentrates Projectile B's momentum transfer into a sharp, high-frequency kinetic spike. We can observe the result of these impulses by looking at the physical depressions left in the gelatin block. Projectile A creates a deep 11 cm cavity, while Projectile B creates a shallow 6.5 cm cavity. In this scenario, Projectile A's deeper tissue penetration carries a severe risk of direct structural damage to the underlying organs. But the human body does not handle all shocks equally. Soft tissues act like low-pass filters, naturally absorbing and dissipating slow mechanical impulses. Projectile B's rigid body slap generates a high-frequency impulse. Soft tissue cannot filter a force that sharp, and the bone tissue underneath will readily transmit it. The energy cannot penetrate deeply. It stays in superficial planes. This risks severe cutaneous effraction, where the plastic body shears the skin. The shallow physical depression left by Projectile B creates a false sense of safety, masking a severe internal shockwave. This exposes the flaw in the 150 joule kinetic energy limit. It is a static metric that fails to account for impulse frequency and the rate of momentum transfer. A sharp deceleration wave like the one from Projectile B can disrupt organ function without leaving a deep wound cavity, creating a serious risk of commotio cordis, sudden cardiac arrest caused by a blunt chest wall impact. Ballistic safety depends on a precise match between a specific launcher and its ammunition, rather than a universal property of the round itself. Changing a projectile without verifying how its center of gravity interacts with the launcher's barrel twist rate can inadvertently create a lethal weapon. Genuine safety requires rigorous, multivariate dynamic analysis of momentum and impulse, rendering arbitrary kinetic energy caps inadequate.